Chapter 5, Integration. We will look over the approximate the area. Before we do that, let's take a look at the summation notation. The sigma notation is of the form of sigma from I equal 1 to n. So I equal 1 is starting point and n is the ending point. So here we have the starting and n is the ending. So the summation of a sub I starting from I equal 1 to n is equal to the sum of a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n. So for example, if I say I want the summation of I from 1 to 6, then I'm looking at 1, 2, 3, 4, 5, 6, right? The property of sigma notation, let a sub 1, a sub 2 to a sub n, and b sub 1 to b sub n represent two sequences of terms, and let c be a constant. The following property hold for all positive integer n and for integer m, with 1 less than equal m less than equal n. So the first property said, if we look at the summation of c repeatedly, this really meant we're looking at c plus c plus c, so on and so forth, c for n time. This really just meant n times c, the summation of n times c. If we have a constant multiply with a term, then we can factor out a constant. The summation of the sum of two sequences equal the sum of each sequences added together. Similar for subtraction. Now the next thing, this is what I want to pay more attention to. Here you're looking at you split in the two terms. Okay, here you we split in the sequences into two separate ones. So if here is n at m, then the starting point of the next summation is m plus 1. Okay. Sum and power of integer. The sum of n integer equal to n times n plus 1 divided by 2. The sum of n integer square equal to n times n plus 1 times n plus 2 divided by 6, and we have the sum of cube. So let's take a look at the next example. We want to evaluate the sum. Here you have, we want to evaluate the sum 3 minus I squared, starting from 1 to 6. We can't really do this one easily, so what I want to do is first I will go ahead and multiply, we'll expand the term out. So I'm looking at I equal 1 to 6 of 9 minus 6i plus I squared. I can use the property of summation to rewrite this as follows. Okay, well, the sum of the first one is just 6 times 9. The second one, I have negative 6. Now note that here n equals 6. Okay, so the second term, I'm looking at 6 times 6 plus 1 divided by 2. Next one, this is I squared, so the sum of I equal 1 to n of I squared, that equal n times m plus 2. We were told that m plus 2, n plus 1 divided by 6. So this is 6 times 6 plus 2 times 6 plus 1 divided by 6. Let's go ahead and simplify this. We get negative 16. I can try the next one. Again, I go ahead and split it in two different parts. Okay. And I will use the summation formula, the result of the summation that we have earlier. So of Q, then we're looking at sit times sit plus 1 over 2 and the square minus sit times sit plus 1 times sit plus 2 divided by sit. So let's go ahead and simplify this. We will get 385. In the next term, well, let's go ahead and see if we can write this out the first couple terms, see what happened. When I equal 1, I'm looking at 1 divided by 1 minus 1 over 2. When I equal 1. When I equal 2, I'm looking at plus 1 over 2 minus 1 over 3. This is I equal 2. When I equal 3, I'm looking at 1 over 3. Okay. So on and so forth. So what happened when I equal to n minus 1? When I equal to n minus 1, I'm looking at 1 over n minus 1 minus 1 over n. When I equal to n, I'm looking at 1 over n minus plus 1, right? So note that all the terms in the middle canceling out. What you really left with in the sequence was just really saying you have 1 minus 1 over n plus 1, where n equals 40. So this is 1 minus 1 over 41. So this is 40 over 41. How do we use this to approximate the area? Okay, so we divide the curve. We divide the area under the curve into small rectangle in order to help us estimate the area of the curve under the curve. So let's see how do we do that. Estimate the area under the curve of f of x equal 1 minus x squared in the interval 0, 1 using the left endpoint for n equal 4. What does it mean by using the left endpoint? So we want to estimate the area in the interval from 0 to 1 using the left endpoint for n equal 4. So let's take a look at what are those points. What are the values for x? So in between the interval from 0 to 1, and we split this into 4 equal parts. The left endpoint would mean we evaluate the function, the f of x at point on the left. These are the left endpoint. So what we're saying here is we estimate the area of the rectangle, of this rectangle, and if I can draw it evenly. Using the left endpoint. Okay. So how do we determine? So we look at the area, the rectangle. We know we first would need to find the width of the rectangle. The width of the rectangle, delta x, is equal to 1/4 times 1 minus 0. That is 0.25, right? So we find the area, we estimate the area of the left is equal to f of 0 plus f of 0.25 plus f of 0.5 plus f of 0.75. We take all that, we multiply with 0.25, that is delta x. So the f of 0 equal 1. So here's our first rectangle. F of 0.5. So here's our second rectangle. Okay. And so we get f of 0, f of 2.5, so of 0.25. So this is the second rectangle. Here's the third rectangle. And here's the fourth rectangle. So we use this to estimate the area under the curve of f of x equal to 1 minus x squared. Now looking at this, we noted that we have an overestimate because we also have because when we draw this rectangle, we have the leftover, right? One that is more than on the curve. So this is the overestimate. And with this estimate, we say that the area under the curve here is equal to 0.78125 unit square. Okay, so we're talking about the area, this area being estimated is that much. Okay, so let's say what happened if we use the right endpoint. So for the right endpoint, again, we're looking at the interval from 0 to 1, and we split it into 4 equal parts. The right endpoint, a point on the right hand side. So these are the right hand side. Delta x in this case is equal to 0.25. Delta x can be solved by taking the endpoint minus the starting point divided by the number of the rectangle. So I'll go ahead and draw the rectangle in. So my right endpoint is at 0.25. So the value of f at 0.25, I'm looking at the smaller rectangle. Okay, and so at 1, we barely really have any rectangle here. Now note that here, we have a gap. These are the gap between the rectangle and the curve. So if the rectangle being drawn and that underneath the curve, here we have an underestimate for the area. The area is calculated by the estimate by 0.25 multiplied with the sum of f of 0.25, f of 0.5, 0.75, f of 1, and this equal to 0.53125. So if you're looking at the earlier problem, we have an overestimate at 0.78125, and now we have an underestimate at 0.53125. This means that the actual area of underneath the curve is somewhere between those two values. Another way of using the estimate is trying to use the midpoint to see if we can actually get a better estimate. So what are the midpoint in this case? Okay. So again, look at the interval from 0 to 1. 0.25, 0.5, 0.75. So the midpoint are the midpoint of these interval. So the midpoint here is 0.125, 0.325, so on and so forth. 0.375, 0.625, 0.875. Okay. So let's draw this in. First, we go ahead and divide our number line into 4 equal parts. And then we put in the midpoint. And we draw our rectangle according to the midpoint. So note that here, let's draw this in. Okay. So our length of the rectangle is of where the midpoint ended. Where the midpoint is. So note that here we cover more of the area under the curve. We still have some over and some under. We still have some gap here, right? However, the gap is smaller. So hopefully this will be our better estimate. So let's go ahead and add all this up. The estimated area was 0.25. The length of each rectangle is still the same. However, the width of each rectangle is still the same. However, the length is different. So we're looking at f of 0.125, f of 0.375, f of 0.625, and f of 0.875. So when we calculate this, we get 0.67185. So this is a little closer estimate of the area under that curve.